Hello, everyone. I'm Chawla Jain. I work with Mecklenburg County as a GIS DBA. And I think it's my honor to introduce the Herb Stout Award winners today. I love the work these students do because it is so innovative and not the routine from where we all come from. So our first speaker today is Courtney Cameron. She holds a bachelor's degree in earth science from Duke University and is an MS candidate and NSF graduate research fellow at North Carolina Central University, where she researches hydroseismicity in the Eastern Tennessee seismic zone and gerrymandering in North Carolina. Courtney, thanks.
All right. Hey, everybody. My name's Courtney. I'm a master's student at North Carolina Central University. So today I'll be talking about some work that I and my department have done with redistricting. Now, of course, North Carolina's been in the news a lot lately for gerrymandering, and you might have had the problem I did that your district moved or your representative changed last year because of court cases and map redrawings and that sort of thing. So what we were looking into is trying to see if we could use ArcGIS to come up with a less biased method of redistricting for congressional seats and hopefully all seats. So what I'm showing here is 3 different House of Representatives federal district maps for 2010, one that was made in 2011 in the center, and then in February 2016, the one that became law following court challenges. So what's interesting about these is from the first 2 especially, it doesn't seem like there's huge changes between them, but just some quick numbers to kind of show you what an influence these districts can have on election outcomes with respect to voting. In the first map in the 2010 election, 54% of votes were cast for Republicans for the House of Representatives, but only 46% of seats, that is 4 out of 13, went to Republicans. And then after the maps were redrawn, the General Assembly flipped, Republicans gained control of both, and they were able to draw the maps, whereas before they'd been drawn by Dems. Sort of the opposite started happening where there was a big gap between the number of votes cast for Democrats and then the seats that they won. And then, of course, now, as I mentioned, this is what our map looks like as of February of last year. And so, as I said, we were trying to use ArcGIS to investigate perhaps better ways for districting than just hoping politicians do the best job. So there's been a lot of work done with this, and these are 3 examples of maps that have already been suggested. The one in the upper left is an optimal proximity map that kind of tries to optimize the center of the district relative to the population around it. The one in the center, shortest split line, just keeps iteratively cutting the state in half using this shortest line it can to keep dividing it into population halves. And then the third one was actually part of many maps drawn by some mathematicians at Duke University using more of a probabilistic method. So they just tried to create 13 districts that were compact and had equal populations. And of course, there's, according to their calculations, 10 to the 785 possibilities for that. And then they ran some numbers comparing election outcomes to what was statistically likely based on what they found here, and pretty much the politicians are coming up with, in terms of election outcomes, very, very, very statistically unlikely maps. So, for example, in over half of their runs, Democrats in the 2012 elections got 7 or 8 seats compared to the either 4 or 3 seats, depending on the year, that Democrats won with the map that was shown before. So our approach is using ArcGIS Network Analyst, the location allocation maximize capacitance coverage, which is, I believe, originally designed to try to optimize where to put stores and that sort of thing to serve populations. And we decided to try to use it for districting where your customers in this case are voters. And then the facilities or stores in this case are districts. And then we're assigning 734,000 people, roughly 1/13 of the state's population, to each district. And so, as it says here, this method in ArcGIS will assign people to districts based on the least impedance, in this case, distance along a network, while optimizing for capacity or population in this case. So for our for our demand points, which is people, we used a census tract data, and then we did two methods. We just converted the polygons to points in one case, and then in another we created a probability raster using population density. And then for the facilities, the stores, or the seed points, or what will you, there's of course an infinite number of possibilities for where you put these 13 points, and we tested three methods. We created one using the spatially balanced points tool using our probability raster, and then the other two we based the points on what those other redistricting methods have used. And so for the two networks, we tried state roads and also a very small, just square grid, a 1,000-foot grid. And then to evaluate the districts, we were using something called the RADWQ quotient, which is comparing the perimeter of the district to the perimeter of the smallest bounding circle. And 1 is a great score, 0 is the worst score. And then we also looked at, was the population between districts equal, were they contiguous, and was it splitting counties? And so for our three the networks and the demand points ended up having next to no effect on the results. So what was very important in our case was those seed points or facilities. So these are the three results for those different facility setups. The first one being spatially balanced. No legal districts were created using this facility setup. None of them were contiguous was the main problem. The population was okay. 2 were illegal in terms of population, and then the average compactness was 0.25, 1 being the best. So this didn't work particularly well. And then for the shortest split line, similar problems with contiguity. We're getting better. There are, in fact, some contiguous districts now. Compactness has improved a lot from 0.25 to 0.46, still having some population issues. And then for the optimal proximity, this was our best result. There were, again, issues with contiguity. Compactness was 0.46, 1 being the best. And once again, we're seeing this issue with population deviations from what it should be. And if you notice in all of these maps, there's sort of white areas, and those were census tracts that weren't being picked up by the software for some reason, which explains to some extent why some of these districts keep having not enough people in them. And so this is just a comparison of our best districts in the upper left, the districts that were in effect until last year, and then the districts that became law last year. And it's sort of interesting that our best districts and the new districts are somewhat similar at first pass, I think. Of course, I have no idea how the map was drawn for the new districts by the General Assembly, but it is interesting that there is some sort of similarity between the two. And so the pros of our ArcGIS network analyst method is that it's pretty simple and fast and flexible. It could be used for any type of districting. You would just have to change your number of facilities or seed points, and you could change the population. It was very good for compactness. Our best score was 0.46 versus for those old districts that were thrown out, the average score was 0.29. And the famous District 12, which is kind of satirized in this Sea Dragon comic, its compactness score was 0.07. And then another possible benefit is that it's reasonably simple to explain to the public, and since it does require sort of interacting with the method by selecting those points, people might like it. Some cons, of course, is one of the benefits in that you select the points, so there is some bias that's introduced there. In ArcGIS specifically, you can't force contiguity, so that's, from a legal perspective, a big issue. So even if you tried ArcGIS, you'd have to manually correct your districts, which is another area for bias to come in. It doesn't respect county boundaries, and there were the software errors with not picking up some people. Probably the worst con for it is that you'd have to sneak the method past politicians, which seems pretty unlikely. And then in terms of going forward with this method in the future, we're considering creating a script to randomly create 13 points over and over, draw the map, evaluate the map that's produced, and then keep doing that until sort of you come up with a good map based on whatever criteria you want to use as a threshold. Trying different networks, so we had pretty dense networks with the state roads and the grid, but maybe a minimalistic network like a polar grid shown here would change what the districts looked like, and relatedly would be reducing the number of demand points, so combining census tracts. Of course, addressing software errors, which might not be possible in ArcGIS because it wasn't designed for this particular use. But maybe instead kind of using this idea as a building point to create a different software, which is what we're working on, to develop a program that the public could use to select 13 points and draw their own districts. And then, of course, it remains to be seen what the legal scene is going to be for districting. There's a case that's going to be seen by the Supreme Court of the United States this year regarding North Carolina's districts and the legality thereof. So depending on the outcome of that, the scene for redistricting could change greatly. And that's all I have, so I'd like to open up for questions. I mean, undoubtedly they do hire consultants. I'm not sure if that's public knowledge, but I mean, at least based on how statistically unlikely these districts are, somebody is obviously very strategically drawing them to achieve certain outcomes. Right. 10 are Republican, 3 are Democrat now. Well, right, in terms of votes cast. This District 12? I don't know what the percentage. This district doesn't exist anymore, but it was a Democratic district. It was probably a packing district. It was designed to pick up as many Democratic voters as they could and kind of sacrifice one district, to the Democrats. Right, exactly. Sure. Well, of course, ideally, the percentage of districts for each would match as closely as possible the percentage of votes cast statewide for each. I haven't run a scenario with, for example, 2016 election data specifically with the districts that I've made, but for the probabilistic districts that I showed earlier from the Duke mathematicians, they did run, not for the latest election, but for the 2012 elections, they did check 100 different basically scenarios with the maps they generated, and then they used voting data for it. And the outcomes they were getting were a lot closer. So if roughly half of the votes were Democrat, and half or more of the districts were going Democrat in their their scenarios. Any other questions? All right, well, thank you for your time.
Next we have Elizabeth Christensen. She holds a master's degree in environmental science and engineering from UNC Chapel Hill School of Public Health. She's currently a PhD student studying how land use affects fecal contamination in NC rivers as a microbiologist. Prior to graduate school, she worked with UNC's Water Institute looking at global access to drinking water, where the work she's presenting is a product. She's talking about water problems in Nigeria.
Thank you, Chawla, and good afternoon, everyone. Get this. There we go. Okay. Great. So this is work that I started in 2012. We published it in 2014. And so I apologize if I look down at my notes a little bit. It's trying to remember this. It's one of my favorite projects I've worked on. It's with the Water Institute at UNC. I wanted to briefly just give a plug for what I'm doing now. My master's was looking at spray field data for industrial swine operations in North Carolina and created a spatial data set for spray fields in Duplin County. Duplin County is the densest place in the world in terms of industrial hog production. And now I am a microbiologist and sampling streams to look at fecal contamination. And so if there are any microbiologists, hydrologists, or agriculture folks in the room, I'd love to talk with you later. Right, so today I'm going to talk about urban definition, especially the geospatial definition of what we mean when we say urban. And this came out of, I was working in an office with Rod Bain, second author here, and he was working with a water quality data set from Nigeria, and I was working on some population data, and we decided to ask the question, well, what would happen if we looked at water quality data and then looked at these definitions of urban and ask the question, does water quality, does access to safe water change based on whether you live in an urban area or whether you're based in a rural area? And so that's how this project started. So first, why is it important to even differentiate urban and rural? Why do we care? One of the reasons is to look at the distribution inequity between urban and rural places, and a lot of people now also look at different economic quintiles in the urban setting and in the rural setting instead of just looking at urban and rural. But a lot of times we think about urban and rural, we think about just trying to compare between an urban place and a rural place. And so the urban poor and rural poor have different vulnerabilities to water access. And so for the urban population, as an example, there's greater reliance on cash income for water and sanitation, but for the rural population, there's an increased travel time. So different vulnerabilities there. Just looking at Google Scholar last night, there's other reasons we care is other people care. So other people care about this urban-rural divide, looking for obesity, tobacco use, and teen birth rates. And in my field as well, sometimes different standards or targets are set for the urban location versus the rural location and urban areas. And that can sometimes cause an urban bias when we set different targets for urban areas versus rural areas. And so that was another reason why we wanted to look at this. And so what do we think of when we say the word urban or rural? And so when I think of urban, initially I thought, well, it's like a city center. You have a lot of people. When I think about rural, I think about agriculture, I think about farms. But when we look at what the UN decides to say is urban or rural, they decide that each country is allowed to decide for themselves what they're going to call urban. And that can take a variety of different, it looks differently depending on the country you're in. And so this is a table just kind of showing, you don't have to read it, but a lot of the different metrics that different countries use to categorize their cities as urban. And so, for example, 118 countries only use administrative boundaries to categorize something as urban. Other countries, 43 countries, say if there's, they identify urban based on the functional nature of the urban area. So if there's paved streets, water supply systems, sewerage systems, and others just look at population density. So depending what country you're in, this definition changes. And so as we're thinking about what is urban and what is rural, it's not quite so black and white as a city center and an agricultural farm. You start to get, if you think about peri-urban areas, so suburbs, which have the built infrastructure but it's lower density, versus a slum, which has high density but not very, very good access to the urban, I guess, higher quality of life. And so our objectives were first to look at 8 different geospatial definitions of urban and to see whether water safety in Nigeria is more related to these urban areas than rural areas or vice versa. Look at the frequency of the metric we were using was thermotolerant coliforms, which is just fecal contamination, in different types of water sources. So the United Nations looks at improved water sources and unimproved water sources, and so we were looking at improved water sources. And then also think about the unimproved water sources, so like surface water compared to like piped water. Okay, so these are 8 different urban definitions. Once I started taking a deeper dive into how people look at how we define urban, it ended up being really interesting. There was kind of a top-down approach to identifying what was urban using remote sensing, and then kind of a bottom-up approach using like census data. And so when we think about these remote sensing methods, on the left, it's this, I have it as kind of a reference, it's called the GRUMP dataset. And it looks at anthropogenic light. And so it tends to overestimate the extent of the urban area and also overestimates wealthier places because they have electricity. Glob Cover and Modis are also products using satellite data, and they're looking for like the built infrastructure. And so that's one way to measure urban. Another way to measure urban is looking at these ground inputs, which this is going to be things like using census data or modeling the population density. And so let's see, Aegiopolis on the left is sort of a combination of using satellite imagery and the ground input methods. And then this Landscan and AfriPop threshold data sets, I created these data sets based on 2 different population density data sets. And so these 2 population density data sets are created, they take the most recently available census data, and then they model it based on different parameters. So for Landscan, they look at the slope of the cell to say if it's really steep, it's mountain, nobody lives there, we're going to X that out and say nobody can live there. They also look at roads and say if you're closer to a road, it's more likely that someone's going to live there, and so we'll model the population density such that even if the census just gives us this homogeneous number over an administrative district, we can model within that administrative district and get a better sense of what the population density is. And so to make these 2 different rural and urban maps using population density alone, what I did is I looked at Nigeria and said, okay, the UN estimates that the proportion of Nigeria that's rural is 50%. Total Nigeria population is 170 million. So if I look at, in this picture, the teal is selected, and so between 0 and 100 people per 100 meters squared is selected in teal. And when you sum up all of the people that live in that teal area, it happens to be only 0.2% of the total population. And so it's much lower than the target 50% that we're looking for. This is now 7% of the population is rural, 34%, 50%, and now we have our map for 50% rural, 50% urban, and this is how I was able to make these bottom 2 urban definitions. So now with these 8 definitions, we have 8 definitions of urban that are getting at different aspects of what the urban environment is. If there's light, if there's the built infrastructure, or if there's a high population density. So after that, we had our water quality data. And this is what we were trying to see if our water quality data changed based on whether it was in an urban location or a rural location. And so the RADWQ survey is, we did not do the survey ourselves. It was given to us from the World Health Organization. And the RADWQ survey is a rapid assessment of drinking water quality for 1,768 samples, and they came from different improved source types. So this is like piped water, dug wells, etc. And we were looking again at thermotolerant coliforms, which is a kind of fecal bacteria. So E. coli is an example of thermotolerant coliforms. So this is an example of one of our results. This would be, we would make something like this for each of the urban definitions, and so this is just for GRUMP. And on the y-axis is the different type of improved source, and the bar graphs along the x-axis are showing the difference between rural and urban, and the proportion of samples that were total fecal coliforms or not, that had the water contamination. And when we put all of this into a table to see, are we seeing differences between urban and rural, we end up finding the columns are the different improved source types, and the rows are the different urban definitions. A value greater than 1 indicates that compliance is higher in urban areas. And so the overall, thing to take away from this is that we didn't see a lot. It was really different between each of the urban sources. The urban didn't mean the same thing for each of the urban data sets. And so when we finally took into account the unimproved water sources, so like Nigerians that are drinking surface water and don't have piped water, this is when we found that in rural areas, about 60% of people in rural areas compared to about 30% in urban areas had a higher fecal contamination in their drinking water. So our results indicated that urban improved sources of a given water source type are no more contaminated than rural ones. So they're, in terms of the improved source type, whether it's piped water in urban areas or piped water in rural areas, our urban data sets didn't show that there was much of a difference, which is important when we're thinking about having different targets or standards for urban areas versus rural areas. We shouldn't. The second is that we found no evidence to justify different urban and rural water quality standards. We did find that fecal contamination was higher in rural areas when we combined the unimproved water sources, so because we took into account everything that Nigerians were drinking. And we found that comparisons of urban and rural areas are very sensitive to the definition of what we call urban. And so I want to conclude with, this is one of my favorite images from this work. So the colors are for each of the 8 data sets. If they were all in agreement, always urban, it's dark red. If they were always in agreement and they were rural, it's dark blue. And everything in between, you start to see this interurban variability. You start to see this urban-rural gradient. And so what I like about this is that although an urban-rural dichotomy is widely used and what we often talk about, a more nuanced continuum using meaningful indicators is more useful. And these indicators can be multifaceted indicators of the urban environment, including the built infrastructure, population density, and access to services. And secondly, incorporating urban and rural subgroups. So not just looking at urban and rural, but looking at subgroups within the urban context and subgroups within the rural context is really important when we're looking at disparities. So I need to thank my co-authors, Rob Bain, who's at the Joint Monitoring Program right now, Jim Wright, who helped a lot with the GIS, Stephen, who had insights from Nigeria, Rafat, who gave us the data set, and Jamie, who let us kind of jump down this rabbit hole and take some time to do this. So, thank you.